Now, introduction. The concepts presented in the previous slides will be extended here and applied to the analysis of beams. It will be shown that once the member stiffness matrix and the transformation matrix have been developed, the procedure for application is exactly the same as that for trusses. So it means the basics are the same, only the member and actions we need to change now. What happens now, in case of the trusses, if you remember, we used to give horizontal translation and vertical translation. Those were the global directions. And we found the member and actions, which were the member and actions, and in turn, those were the stiffness coefficient elements. Now, in case of the beam, what happens? We have two kinds of now member and actions. One is the shear and the other is the bending moment. Axial force is not going to be there. If we include the axial force also, that is known as the frame element, 2D frame element. In a way, we can say that frame element, it is a combination of the truss and beam element. Why truss? Because axial action is coming from the truss, and the shear and bending moment, they are coming from the beam. So the stiffness matrix, now we will generate the stiffness matrix. And once we generate this stiffness matrix, rest of the procedure is the same as we discussed in case of the pin jointed frames. Now, before developing a formal procedure for applying the direct stiffness method, it is first necessary to establish some preliminary definitions and concepts. First, we will discuss about the member and node identification. So again, it is the same. If you remember, in case of the pin jointed frame, the node numbering was given a number enclosed in a circle, and member was identified by a number within a square. So then we discuss the local and global coordinates, kinematic indeterminacy, and elemental and structural stiffness matrices. So coming to the member and node identification, in order to apply the stiffness method to beams, we must first determine how to subdivide the beam into its component finite elements. Again, we will be going towards the discretization of the structure, that is dividing the structure into finite elements. Now, how those are done? In general, each element must be free from load and have a prismatic cross-section. This will be the property of an element. It will be having uniform cross-sectional area throughout the length. It is known as prismatic. And within the member, we are not going to have a pointed load. It can have a UDL, but not a pointed load. If a point load is coming, we will take that as a node, and on either side, we will be having the elements. For this reason, the nodes of each element are located at a support. At a support, what is happening? It is acting as a pointed reaction now. So pointed load is coming, so we take that as a node. And at points where members are connected together, if different cross-sectional area, different material members, if they are connected together, so that point also we take as a node. Means a different element, or it is the end of an element, that point, that specific point. Where an external force is applied. Now, if an external point load is applied at a point, so again we take that as a node or child. Where the cross-sectional area suddenly changes, again, if we have non-prismatic situation, cross-sectional area is suddenly changing, so we take that also as a node. or where the vertical or rotational displacement at a point is to be determined, or let's say prismatic condition UDL, but you are now interested at some specific point that let me find out now the vertical displacement or rotation at that particular point, so we consider that one also as our node. So these are now the different criteria how we decide about a node in a structure. Now here, member and node identification. With the help of this sketch, now we are going to now define these things. Now from the left, if you see within circle, first if you see along the horizontal, we have x-axis, along this y at this node 1 within the circle, we have y-axis. So this is origin node 1 within the circle. In the middle, we have node 2, and then under the pointed load, we have node 3, and then at the extreme right, we have node 4. So now, if you see how these nodes are taken, it's this member is this whole structure. It is of the same material having uniform cross-sectional area. But at 1, if you see, we have a support condition, so we define this as a node. At 2, if you see again a roller support now, support is coming, so again we define this as a node. At 3, if you see a pointed load P downward, so again we take this as a node. And then at 4, if you see again we have a roller support, so because of the support we take this as a node. 4 nodes we need to now describe this structure. 4 nodes, and within, if you see from node 1 to 2, we can take this element 1. So you can see in this square as 1. Between 2 to 3 we have 2, and then from 3 to 4 we have member 3. Also you can see the connectivity with these arrows. Member 1 start is 1, end is 2 now. So member 1 definition going from 1 to 2. 2, this arrow is again showing it is from 2 to 3, and member 3, it is from this 3 to 4. Then you can see without circles and without these squares, these numbers, these are showing the kinematic indeterminacy now. How we are going to proceed? We take start from the free, now degree of freedom, the joints who are free to move. Now this one, if you see, this one is a rotation which is free now displacement at this giant 4. So we start from the free, this is free, so it is 1. What else is free? If you see at P, it can now, this joint can displace in the vertical direction as well as it can rotate also. So vertical displacement we show by 3, but and this rotation we show by 4. This joint 2, if you see, it can rotate. So here we are showing 2. And this joint 1 now again, if it can rotate, so this is giant. So how it is done now? First we look at the support conditions. So support conditions, if you look, this 4, it can rotate now, free to rotate. So 1, then 2, it is free to rotate. It is 2, then at 3, we have vertical displacement. So it is 3, rotation at 3, again it is free. So this is 4. Then we are coming now, the free, it is going to be followed by the now restrained displacements. At 1, it is a fixed support now, so it is restraining the rotation as well as the vertical translation also. 5 and 6, then at 2, the vertical displacement is restrained now, so it is 7, and then at 4, the vertical displacement, it is our 8. So it is an 8 degrees kinematically indeterminate problem if we remove the support conditions. And how this labeling of displacement is done? We start with the free followed by the restraint displacements. Free work, if you look at again at this joint 4, you can start from anywhere, let's say from 2 if you are taking start. So this rotation we take 1, then let's say these under this 3 we take 2 and 3, 4, and then we come to the restrained one, 5, 6, 7, 8, whatever order, but free first and then followed by the restrained displacements. We have 4 joints, 2 displacement possible at each one. So this way it is becoming total 8 degrees kinematically indeterminate problem. So using the scheme as that of trusses, 4 nodes are specified. We discussed 1 up to 4. Numerically within a circle. So numerical values within the circle, these are the labeling for these nodes. And the 3 elements are identified numerically within a square. So the square numbers are showing the element numbers. Also notice that the near and far end of each element are identified by arrows written alongside each element. So you can see these arrows also, which is showing you the connectivity. Going to the next slide now, again, local and global coordinates. In beam, if you see, beam is shown most of the time horizontal, and our global x-axis, it is also horizontal. So it means our local and global system will be matching. Means in this case, we will not be needing any transformation or rotation matrix. It will be one also rotation matrix. So local and global coordinates, let's discuss this. This is our topic 2 now. The global coordinate system will be identified using x, y, and z axes that generally have their origin at a node and are positioned so that the nodes at other points on the beam all have positive coordinates. At starting point, we'll be coming and taking this origin, and then we direct our x, y, and z in the positive directions. The local are member which are x prime, y prime, z prime coordinates have their sign at the near end of each element, and the positive axis is directed towards the far end. So here you can see now the local axis 2 to 3. This was the starting node was 2. This is 3. This is for element 2. And here you can see the x prime and y prime. These are the local axis system, and you can see the positive direction. Now notice that for each beam element, the x and axis will be collinear, and the x axis will be collinear, and the global and member coordinates will all be parallel. Therefore, unlike the case of trusses, we will not need to develop transformation matrices between these coordinate systems. Already they are parallel, so we don't need to develop the transformation. And what was the transformation in case of the pin jointed frames? It was cos theta, sin theta, 0, 0, 0, 0, cos theta, and sin theta. This was in the second row. Then we don't need it here. Now, kinematic indeterminacy of beams, again, you will be looking for the free joints, and the joint numbers, and each will be having 2 degrees of freedom. One will be the vertical translation, and one will be the rotation at their joint. But if there is a pin now joint, so at pin joint, it can give you 2 independent rotations. So 2 independent rotations. From rotations, you have 2 degrees kinematic indeterminacy, and there will be a 1 vertical translation. So it will provide you 3 degrees of kinematic indeterminacy. Now, if we consider the effects of both bending and shear we consider in case of the beam elements. then each node on a beam can have 2 degrees of freedom. Each node will be having 2 degrees of freedom, namely a vertical displacement and a rotation. So here again you see now 1, 2, 3. We have 3 element this structure, which is a beam in this case, and we have four nodes. This is node 1, node 2 under the point load, then at the pin. Again now it's different members are meeting here, so we can consider this as a node. So this is node 3, and then the end point where we have a support, this is 4 now. The displacements now, if we are starting again from the free joint, so it can vertically translate this joint 3. So vertical displacement is 1, rotation to the left it is 2, rotation to the right it is 3. Let's look for the other free rotations now. So this node 2 where we have the point load, it can displace in the vertical direction as well as it can rotate also. So 4 and 5 displacements are coming from here. Then we come to the restrained now joint displacement. So 6 and 7 at joint 4, and then 8 and 9 at joint 1. So it is 8 degrees kinematic, 9 degrees kinematically indeterminate problem. We have 4 nodes, but because of the pin joint condition at this node 3, we have one additional rotation. Because of this, it is becoming 9 degrees kinematically indeterminate problem. Now, element and structural stiffness matrices, already we discussed this in case of the trusses. So development of stiffness matrix for beams follows a similar procedure as that used for trusses. First, we must establish the stiffness matrix for each element, and then these matrices are combined to form the beam or structural stiffness matrix. So again, for a particular element, we will develop its elemental stiffness matrix, and those elemental stiffness matrices will then be combined to form the structural stiffness matrix. To develop the stiffness matrix for a beam element or member having a constant cross-sectional area and reference from the local x, y, and z prime coordinate system shown in figure on next slide. So here you can see now what we are going to do now. Positive sign convention is shown here. This left is the near end, and then right one is the far end, and connectivity is shown with the help of this arrow now. Now Q we use for the action produced now, and D we show for the displacement produced. So and prime we show for the local coordinate system. So x prime and y prime, you can see this is the local coordinate system. At the near end now you see the subscript becomes this n. This is the near end. Q show the action now, and which one action? The moment produced at the end. And then this Q and Z, it shows the vertical reaction now produced. So this Z we show for the Z direction. So about the Z direction we have a moment. So moment will be Q and Z prime. And the vertical reaction produced, it will be Q and Y prime. So Q is this Q with Y. It is showing the vertical reaction, which is shear. And then the Q and Z, it is showing the moment. Now, correspondingly now, the vertical now displacement will be shown by D and Y, and the rotation will be shown by D and Z. So it is actually theta now, theta n you can say to this arrow. It is showing theta n as well as it is showing mz. And the vertical reaction usually we show for the shear V. So this is your Vy and this is your displacement delta Y actually. So this is the normal notation we used to use. So now at the far end again, Q is for the action produced and D is for the displacement produced. With the Y subscript, it is showing the translation, or it is showing the shear now. QFY, it is now the shear produced at the far end in the Y direction. And D is the displacement produced at the far end in the Y direction. QFZ, Q, this is now action produced about the Z axis at the far end. And D is the displacement produced. Displacement, because of this, is going to be the rotation now at the far end, Z axis. What is going on? Somebody has turned on the mic, so could you please turn off the mic, please? If you have any question, you can ask me. Otherwise, you should turn off your mic. Okay, so there are now, coming to now the description of these notations. There are two reactions at each end of the element. Which one are those two reactions? One is shear and one is moment. Consisting of shear force, here now you see QFY and QNY. QFY and QNY at the near end and at the far end along the Y direction, and bending moments now QNZ prime and QFZ prime. These loadings all act in the positive direction. So positive directions, counterclockwise moment we take positive, this is our sign convention now, and shear looking in these upward directions, those we take as positive. Linear and angular displacements associated with these loadings also follow this same positive sign convention. So again, rotation counterclockwise, it will be positive, and displacement in the upward direction, we will take that as positive. So from here now, we fix our positive sign convention. You can see for the moment, correspondingly for the rotation, for the shear, and correspondingly for the vertical translation. Here now again that concept is shown. We will now impose each of these displacements separately and then determine the loadings acting on the member caused by each displacement. So what we do now, when we generate the members, this stiffness coefficient matrix, turn by turn, we will be giving now the displacement. We start with the rotation. So at one end, we will allow the rotation, unit rotation, and find out the end actions. And already we found if we give a rotation now at the near end 4EI theta over L, at the far end it will be 2EI or theta over L. Directions are the same. Similarly, we find out the balancing couple now, and that is becoming the shear end actions. So now here now you can see displacement in Y direction. First what we do, we go and give along the Y axis a unit displacement. So when a positive displacement D and Y prime, here you can see D and Y prime at the near end we allow, and how you can give it when you provide a roller guide here, you can move it in the up down direction. As our positive direction is up one now along the Y prime, so what we do, we slide this in the upward direction, and in case of the stiffness coefficient matrix, what we do, we give a unit now displacement and the corresponding member and actions, those are becoming the stiffness coefficient values. So D and Y prime is imposed while other possible displacements are prevented. So you see here it is not allowing rotation, it is only providing this vertical translation. At the far end, if you see, it is a fixed one, so it is not allowing a vertical translation as well as it is not allowing any rotation. So other displacements are prevented except this along the near end, we are providing only the sliding. The resulting shear forces and bending moments that are created are shown in figure A below. So figure A will show. Likewise, when dFy is imposed, the required shear displacement and bending moments are given in figure B. So then at the far end, this sliding is given and then the member end actions are calculated. So coming to the A figure now, as I said, along the y-axis at the near end translation is given. What will be the moment generated now here? The moment generated will be 6EI delta divided by L square. This is the same equation now, if you remember. Do you have any question about this thing? Why this is counterclockwise? Because it is trying to come back to its position now. Already we discussed this in the standard stiffness method. Delta is given. Because of the delta, the moment at the near end produced will be 6EI delta divided by L square. So this is how we get this one. The direction already I described. At the far end, the action, you will have the same amount of action and the same direction. So again, you see 6EI delta or L square. So again, 6EI delta or L square. Remember now, end reactions are the balancing couple. It will be in the counter now direction. So the balancing couple is now, if you see, it was counterclockwise, the both member these moments produce. So to balance this, we need a balancing couple in the clockwise direction. What will be the magnitude? Its magnitude will be the unbalanced moment divided by the length between the two nodes now. So it will become 12EI divided by L square. Direction are known now and its magnitude also known, the shear, which is 12EI divided by L cube and 12EI divided by L cube here for this arrow. Now, if you want to make the first column of the stiffness coefficient matrix, so this sketch will give you the information. Displacement was given in the one direction, and the one direction was the vertical translation. This was D1 now. So corresponding to this, the action produced will be your S11 now, which is 12EI divided by L cube. Let's D2 is the rotation here. So your S21 will become equal to 6EI divided by L square. Now D3 was in the upward direction here, the translation in the upward direction. So that will become minus 6EI. This will become minus 12EI divided by L cube. This one corresponding to D3 now. And let's rotation here. This was D4. So it will become 6EI divided by L square. So if you want to note it down, let's say this is our sign. Now this is the labeling now. Here the vertical translation D1, followed by the rotation here D2, followed by the translation here D3, and followed by the rotation here D4. These are now our displacements, joint displacements assumed. So the corresponding actions you can pick from here, and that will now formulate, that will give you the first column of the stiffness coefficient matrix. Now, if we give the same translation here, so what will happen at the near end now, it is again trying to come back to its position. So this is giving you the sign of this moment now. It will be again because of delta now we are finding out the member end action. So 6EI divided by L square. At the far end again 6EI divided by L square. The balancing couple now, it is in the clockwise direction, the unbalanced couple. The balancing couple will be in the counterclockwise direction. So these arrows again you can see with 12EI divided by L cube, and here we have again 12EI divided by L cube. So this is, as a matter of fact, from here now we are generating the third column of the stiffness coefficient matrix, but we have shown them together on the same slide because we are now discussing the vertical translation given, and as a result member and actions produced. So this diagram will help you in the generation of the third column of the stiffness coefficient matrix. Now rotation is left. So rotation here now you see at the near end, if we provide now in the counterclockwise direction, this rotation. This rotation, if we provide this in the counterclockwise direction, how much now member and moment will be produced? 4EI divided by L. At the far end, it will be the same direction, but half of this magnitude, so 2EI over L. This is counterclockwise, this is counterclockwise, the unbalanced moment is counterclockwise, so balancing moment will be in the clockwise direction. So here the clockwise direction you see, and that is 6EI divided by L square. Again, 6EI theta divided by L square, if you remember, 4EI and 2EI, those were the famous relations because of the rotation given at an end and preventing all kind of displacement at the other locations. So those were the member and actions produced. And similarly, now when we give this rotation at the far end, so again the same kind of now these member and actions 4EI, 2EI, and 6EI, those are now produced. So this will help you to find out this A sketch here. It will give you the second column, and this will give you the fourth column. So when a positive rotation dnz is dnz, when you see the z, it is about the z-axis, which is moment or rotation, is imposed while other possible displacements are prevented. The resulting shear forces and bending moment that are created are shown in figure A below. Likewise, when dfz is imposed, the required shear forces and bending moments are given in figure this one. And now we are in a position to write our stiffness coefficient matrix. So here now you see, this is when the vertical translation was given at the near end. So here now you see 12EI, 6EI, minus 12, and this one. This when the rotation was given at the near end. This when the vertical translation was given at the far end, and this when the rotation was given at the far end. Now with this much, now you remember this equation. If you remember, when we generated this in the pin jointed frame, so it was coming EA or L square, and within the bracket we were having cos square theta, and then cos sine minus cos square and minus cos sine, something like that, if you remember. Now this is the beam element stiffness coefficient matrix. Now you can turn on your mics. This is very important relation. Rest of the procedure is exactly the same. Now here what you will be doing again, you will be identifying your element, its connectivity with the nodes, and then accordingly now you are coming here and you are just putting the member length here, E and I corresponding values, and already you have these coefficients now. So far and you are giving at the top the addresses also. The addresses are coming from the joint displacements at their particular element. And when the element stiffness matrix is generated, then you are combining them, you are adding them by the simple principle. The same addresses will go to the same location. So now you let me know if you have any question. You can turn on your mics. And the only thing here now, you need to work on the generation of this element stiffness matrix, how it is generated. The procedure is the same. Turn by turn, you are giving the displacement and finding out the corresponding member and actions. Any question?
It's clear, sir.
Clear? Okay, so let's go to the next one then. Now, element and structural stiffness matrices. Now, the structural stiffness matrix can be constructed by combining the element stiffness matrix as explained in trusses. So it is exactly the same procedure. Now, application of direct stiffness method for beam analysis. So this is the continuation of the topic. Now you can see now the equilibrium equation. After the structural stiffness matrix is determined, the load at the nodes of the members can be related to the displacement using the structural stiffness equation. Q is equal to, this Q is exactly the same that A now, if you remember. A is equal to S times D, or you can say Q is equal to K times D. When you come across the different books, therefore, action, sometimes they are using A, sometimes they are using Q. For the stiffness, sometimes they are using S, sometimes they are using K. For the displacement, sometimes they are using delta and theta, sometimes they are using the general rotation of D. Here, Q and D are column matrices that represent both the known and unknown loads and displacement. So Q is for the load and this. Now, remember when we say load, so it will be including the member and reactions are support reactions, or it will be the using, or it will be showing the loads acting on the nodes. Now, coming to the problem now, here you see this sketch A, which is showing an overhang beam now. And what is asked now in this, determine the reaction at the supports of the beam shown in figure. EI is constant. Now first we need to identify the nodes now. So supports, for sure each support is becoming your node now. Where the pointed load is applied, abrupt change in load you are having, so that is becoming, so it is a 3-node problem now. You can now put as many nodes as you want, but minimum requirement is 3 nodes. We can define this problem with 3 nodes and 2 elements. If somebody is asking you that in the middle of these supports, now you give me the displacement, so that is also becoming your node now, because you have your interest now there, that how much is going to be the displacement at that specific point. If somebody is asking at 1/3, let's say here at 1/3 between the supports, so that 1/3 point, that is also becoming a node now. But for solution of the problem here, the minimum requirement is that it will be having 3 nodes and 2 elements. Rest the values then you can find out with the help of the interpolation. So you draw this sketch quickly now, and then we are going to explain now how we give it the node numbering and the element numbers, and how we develop the element stiffness coefficient matrices, and then the structural stiffness coefficient matrix. So you take out your pen or pencil and draw the sketch quickly. Just draw a line diagram for this one. 2 meters and 2 meters, and then at the free end you show a 5 kilonewton load downward. Okay, so we move to the next slide now. Here now, free giant was which one, where we can show the free displacements? It was the free end now. So we start with, let's say, the rotation. It is 1, followed by the vertical, this displacement, it is 2. Now rotation at this node 2 is also free, so 3. And then we come towards the restrained one. So here the rotation is 4. Then we have this 5, and here we have 6. So numbering, it is up to you now, but the order which we will prefer, free followed by the this constrained one. Free are now at giant 3, so we start with rotation followed by the vertical, and then here this rotation was free, so it is 3 now. This rotation 4, vertical translation here, this one is 5, this is 6. You can take this 5, this 6, it is your choice. So, and the member numbers now, the member node numbers 1, 2, and 3, from left to right we are moving. Again, these are arbitrary, you can take any one node numbering which you like. Member 1, here you see from node 1 to 2, and member. Now, remember now, if we write the addresses of element 1 now, stiffness coefficient matrix, so what will be the address now? It will be 4, it will be how the matrix was produced now, the stiffness coefficient matrix, which we develop. Translation followed by the rotation. Now remember that order is important. The first column was coming from the translation and then followed by the rotation. So our address now will become 6 4, not 4 6. It will be 6 4 5 3. And for element 2, it will become 5 3 and 2 1. Why? Because it was vertical displacement followed by the rotation at the specific node. That was the order for developing the stiffness element stiffness coefficient matrix. Why this kinematic indeterminacy is 6? We ignore the support conditions and we have 3 joints, so 3 multiplied by 2 now possible displacements. So 3 times 2 is 6. That's why we say it is 6 degrees. So again, quickly now you write down the node numbers, the element numbers, and then the these displacement numbers. So that when we write the addresses for the element, these stiffness coefficient matrix, so that you know how these are coming. So step number 1 is remove all the joint restraints, then determine the degree of freedom and find global displacement in X and Y directions. It will be global displacement in X and Z directions. Actually, rotation is the Z direction. And this vertical is the Y direction. So it should be in Y and Z directions. You see the element connectivity also. Element 1 we say from joint 1 to 2 and element 2 we say from joint 2 to 3. Again, remember this element numbering, how it is done. Free is giving the preference followed by the restrained one, and the order that is your choice. Now you have the flexibility, whatever now for the free you assume and whatever you assume for the restrained one. Here now, if you see, we have 6 displacements we were having. So look, the first one were free. So when we see D1, D2, D3, D4, these were free. Let's go back to this now. You see here 1 rotation free. This one is free. This 3 is free, and 4, this rotation is also free. So these 4 now displacements were free. So free means we don't know how much it is going to displace now. So we put the question marks. Those are becoming our unknown. And restraints were this vertical displacement, it is 0. This 6 displacement, this vertical displacement at joint 1, again, it is 0. So these are known ones. So straight away for D5 and D6, we can put 0, 0. And this is how you see here, D5 is equal to 0, D6. And those free joint displacements, we put them with the question marks. Now Q2, which is corresponding to D2, now we have an externally applied load now here. You see here, this was our D2. So corresponding to this, we have this 5 kilonewton, but this is in the opposite direction. Magnitude is 5. So we put this with the negative sign. So here now we put this negative sign. How much is going to be this Q1 now? Q1, we don't have any external applied moment here. So we put that equal to 0. How much is the rotation here? Now moment here corresponding to this rotation, this D3, it is 0. How much is corresponding to this one now, the moment applied? It is again 0. But now coming here now, corresponding to this 5, how much is the support reaction? We don't know, so we put a question mark. Again here we put a question mark. Or here, if you want to find out the moment now, so that moment here you see 0, 0, and these vertical reaction we have shown D5, D6, these are the question marks now. So now you know the reason here that these are 0, 0, 0, and this is -5 and why question marks, because the vertical support reactions we need to find out, so we show them by the question marks. So Q is the joint force and moment, and D is the joint displacement. So how we make the displacement vector and how we make this load vector now, so it should be clear. Next, now the stiffness coefficient matrix we are coming. This was the standard format. It was because of the NY, it was because of the NZ, it was because of the FY, and this is because of the FC. This was generated. So first now we come to element number 1 now. Now you should be looking at your now that sketch now where we have given the node numbering, the element numbering, and then the displacement numbering. So as I said, it should be 4, 6, 5, 3 for element 1 now, K1. You can see now. And this should be the same order, 6, 4, 5, 3. You see now, if you want to confirm this 6, 4, 5, 3, 6, 4, 5, 3. So here element 1, 6, 4, 5, 3. Again, I'm saying you cannot put, if you are using those element now, element coefficient values, so you cannot use 4, 6. Why? Because first translation was given. So translation, this vertical will be coming first, followed by the rotation, 6, 4, 5, 3. And here it will become 5, 3, and 2, 1. So let's see now. This is 5, 3, 2, 1. You see here, you see. But now if you say that my connectivity, let's say for element 2, it is from 3 to 2, then your stiffness coefficient matrix will, or the address will be 2, 1, 5, 3. That will become 2, 1, and 5, 3. So now it is just a matter of putting the numbers. You have E, you have I, and you have L values, and you have the specific coefficients also. So this is how these values are. If you want to confirm this one, let's confirm this 6 element 1.5, how this is coming. So we come to the basic equation. 12 EI was constant, so this becomes 12 divided by this L cube. L for element 1 was 2 now, so it is becoming 2 times 2 times 2, which is 8 now. So 12 divided by 8. How much is 12 divided by 8? It is 1.5. This is how we get this 1.5 here. If you want to confirm the second one, so second one is coming 6 EI divided by L square. So 6 and 2 square means it is 6 divided by 4. So again 1.5. This is how 1.5. Similarly, the rest now. For element 2 now, the address is given. So correspondingly, you can use your EI, the coefficients, and L values, and you can generate this K2 element. Now, from here now, let me tell you, now we will be going to the structural stiffness matrix. So the order there will be 6 cross 6 because we are having 2 nodes. The kinematic indeterminacy of the structure is 6 degrees. So it will be 6 cross 6. Let's now see from here what will be 5, 5 element there. From here, let me find out. Here you can see the length, everything is given. This will help you in calculation of these K1 and K2 matrices. 5, 5, if you see here, so 5, 5, we are now calculating the 5, 5 of the structural stiffness matrix. So here 5, 5 is 1.5, and here 5, 5 is 1.5. This is, so it should be 3 now. So let's see now. This is, and where is 5, 5 now? This is 5, 5. This is 5, 5 now. This, and you see it is 3. So this is how now the structural stiffness matrix, by adding the K1 and K2, it is generated. So it's exactly the same procedure we did in case of the pin jointed frames. Next, we go now and we partition the matrix again by the same principle. Now, how we delete the rows, how we delete the columns. Now, free joint is accommodated here, these first 4 rows and first 4 columns. We need to multiply these with D1, D2, D3, D4 and get, now here you have 0, minus 5, 0, 0. Only unknowns are D1, D2, D3, D4. So we can find out the values of D1, D2, D3 and D4 by solving this upper left this partition matrix, multiplying this by the D1, D2, D3, D4, and by running these numbers you can find out the unknowns. And then we are coming to these one to find out the unknown now support reactions. So here this left partition, this is of our now use now, and here we use these equilibrium equation now. So action is equal to stiffness matrix times the displacement. Now these are the simultaneous equations now from that partition matrix, and this is how we solve for D1, D2 and D3. So D1, D2, D3 are known now. Next, we for the Q5 and Q6, so those support reactions are also known. Now we are done with this problem number 1 about the beam now. Support reactions are found. When support reactions are found, rest you can draw your shear force and bending moment diagrams now with the help of this problem. Now let me know if you have any question.
Clear.
Can I go ahead now?
Yes, sir.
Okay.
Yes, sir.
So let's go to the next problem, and that is going to be quick now. Here now you see now, first now looking at this figure, it should be coming in your mind that how we are going to split now this into elements, how we are going to discretize this structure now. So in the middle you see a pin connection, so we need to take that one as a joint. At the end we have support, so we need to take those also as a joint or nodes now. Nodes means we have 3 nodes now in this beam, and 3 nodes means we can now split this into 2 elements. So element 1 and 2 you see. Only M naught is applied at the right hand side. So the problem is determine the internal shear and moment in member 1. In member 1 they are asking of the compound beam. Compound 2 members are joined together by this pin connection shown in figure. EI is constant, and you see the loading also at the far end. So you should quickly draw a line diagram for this one. At the left show fixed support, at the right you show as roller support, in the middle you show a hinge now, and at the right clockwise direction M naught you show length of each member is L quickly, and right EI is equal to constant. First, what we do now, we label the joints now. So as I said, 1, 2 and 3 you can see it. Then you can see in the circle were the node numbers, and the squares we have the element numbers, and then we have the joint displacements now. So free joint displacements we start from the pin now. At the left we have rotation 1, at the right of the joint we have rotation 2, and vertical translation we have 3 now. So 3 possible displacement at the pin joint we show with 1, 2 and 3. And you see the sign also, the positive. What was the positive sign? Upward and clockwise, that was our positive. So we show all unknown now joint displacements in their positive direction. Why? Based on this, our element stiffness coefficient matrix was generated. That is important. Here, then you don't have the liberty that you now assume in the downward direction or clockwise, because you will be using that one. If you want to use clockwise and downward, something like that, so you need to generate the element stiffness coefficient matrix accordingly. Then you can use this sign convention. Then rotation at 3, this is free now, rotation here. So we show this by 4 here, you see. And then we come towards the restrained one. So vertical displacement at joint 3, so 5. And then we come here 6 and then 7. So why 7 degrees? The 7th degree it is becoming because of this pen condition. We get one extra indeterminacy. So kinematically this problem, although it is having 3 joints, 3 nodes, so it is not like 3 times 2 now, it is 3 times 2 plus 1 this additional condition because of the pen now. So that is why it is becoming 7 degrees kinematically indeterminate problem. Here you can see it. Now here all the description you can read by yourself. Now Q1, first let's start from the displacements now. So 4 displacements were free as we discussed, 3 at the pin joint and 1 here at joint 3, which is the right one, this rotation. So we put them with the question marks and rest are 0 now. If you see here, 6 and 7 displacement at joint 1 because of the support conditions, they are 0. And similarly, vertical translation at joint 3, which is our D5, that is also 0. So 5, 6, 7, they are 0. And the rest are 0 now. So here 5, 6, 7, you see these are 0. And the rest are unknown. So we put them unknown. Corresponding now, if you see here, D1, D2, and D3, these are 0. Q1, Q2, and Q. Corresponding to D1, if you see, corresponding to D1, we don't have any externally applied moment. Corresponding to D2, we don't have any external. Corresponding to D3, we don't have any external applied. Now, action applied. If we apply, let's say, a 2 kip load downward, so your Q3 will become equal to -3 now, because the load applied here at this point is 3 downward, so that will become -3. So here now you can see. Corresponding to D4, we are having now y minus m naught. If you see here, our assume now positive is counterclockwise, but the m naught at corresponding m naught is in the clockwise direction. So our Q4 is becoming -m naught. That is why we put this in. Now, against the 0 displacement, what we are having? We are having reactions now which are unknown at this stage, so that is why we put. The sample relation is now against these question marks, you need to look at the loads now. If loads are given, if they are in the same direction, so you put them exactly the same numbers. If they are in the opposite direction corresponding, so you put those values with the negative. And if there are no corresponding actions, you put them equal to 0. And here against the 0 displacements now, these 0 displacements will be coming because of some reactions now, which we don't know at this stage, so we put the question marks. So again, Q is for the joint forces or moments and D is for the joint displacements. Here again, we see the standard format of the stiffness coefficient matrix, the element stiffness coefficient matrix. And now we have 2 elements, so we need to put now 6, 7, 3, 1. Let's verify this for K1 now for element 1, 6, 7, 3, 1. So let me go back there. And here if you see, so this is 6, 7, and 3, 1. So that is okay. 6, 7, 3, 1. Translation followed by the rotation. 6, 7, 3, 1. And here for element 2 now, it will be 3, 2, 5, 4. Let's see now. 3, 2, 5, 4. So what will be the order of the structural stiffness matrix now? Kinematic indeterminacy was 7 degrees, so it is going to be 7 cross 7. So here now this is 1, 2, 3, 4, 5, 6, 7. Corresponding addresses, they are coming to their appropriate location now. And this is how this structural stiffness matrix is formulated. You see now 7 rows and 7 columns here from this side. You should start writing this 1, 2, 3, 4, 5 at the side also, so that you know each element. Like what will be the address of this one? This is going to be 6 and 6 row and 6 columns, so it will be 6 6 element. This will be 6 5, this will be 6 4, and similarly this is 6 1 now. So you should know the address. And how can you do it easily? You can do it by writing the row numbers also. The column numbers are given, but you should be having the row numbers also. After this, what we do, we write the equilibrium equation. We partition them. How partitioning is done? Again, free joints and restrained joints. And from here, we are going to find out the unknown joint displacements. For here, we are going to find out the unknown. From this lower left matrix, we are going to find out the unknown reactions. And they are done here. In the next slide, simultaneous equations, solving of the simultaneous equation, which is simple mathematical subject now. So D1, D2, D3, and D4 are known now in terms of the M naught. And then we go and find out Q5 and those Q6 and Q7 also. So now note is given, do practice on problems from Hebler book. This you need to do now. And with this, we finish the this direct stiffness method, and we have applied this to 2 kinds of elements now, 2 kinds of structures, pin jointed frames and the beam one. We are not going to do it for the plane frames and then the grids and then the space now pin jointed frames and the space rigid joint frames, 3-dimensional I'm talking about, because that is going to be in the higher level on your postgraduate level. So till now, this is good enough for you to learn. Now you can turn on your mics and you can start asking me questions. I'm available now. After this, we will decide how to proceed. Whether we should go next now topic, which is going to be introduction to the finite element analysis, which is now more improvement on this direct stiffness method, now more organized way and for more complex kind of structures now. We can analyze the one-dimensional structure, we can analyze the plates and shells, 2-dimensional structures, or we can 3-dimensional structures also, the solid structures also. So now let's